Welcome to a new episode.
Hello and welcome back to the Copper Connection podcast with me, as always, your host Chris Bailey. And today we're levelling up. This is one of these episodes that separates someone who's just installing kits from someone who's actually understanding it. Because let me ask you something. Have you ever been on site? Something's not worked and someone says, yeah, just swap that part. And you're thinking, but why did it fail in the first place? Well, that's what today's about. Today's episode, we're diving into the heart of building service engineering, specifically the mechanical principles of the components we use every single day. Now, I know mechanical principles sounds like something that belongs in a dusty textbook. But trust me, if you want to be more than just a part swapper, you've got to understand the why behind the gear. So today we're talking fans, pumps, burners, heat pumps, controls, all the stuff that makes buildings actually work. And by the end of this, you should be able to walk into a plant room and not feel lost. You should feel like you belong there. So let's get into this week's episode.
Don't forget to hit that subscribe button.
So let's start with air, because before you even touch a water system, you'll run into ventilation. Now, centrifugal fans. Picture this. You're in a big commercial building, offices, maybe a hospital, maybe a school. There's ductwork everywhere, twisting, turning, and massively long runs. You can't just push air through that with a basic fan. There's resistance, friction from the duct walls, bends, grills and filters. That's where centrifugal fans come in. They don't just move air, they build pressure. Here's what's actually happening. The impeller spins, it creates a low pressure zone in the centre, air gets sucked in, then flung outwards by the centrifugal force and pushed into the duct at high pressure. It's like spinning a water bucket. Everything gets forced outwards. Now, here's the key learning point. These fans are designed to overcome resistance. So when you are sizing or diagnosing one, you're not just thinking about airflow. You're thinking about how long is the duct run, how many bends, and are there filters blocking the flow? Because if the pressure isn't enough, the system fails. It's as simple as that. Now, let's compare that with axial fans. These are your straight through fans. Air goes in one side, out the other side, like a propeller. You'll find these in bathrooms, computer systems, small ventilation setups. They move a lot of air, but at low pressure. So here's a rule to remember. Centrifugal equals high pressure, low volume, and axial equals high volume, low pressure. Now, here's a real world situation. You're installing an axial fan where a centrifugal fan should be. The system might look right, it's working, but airflow at the vents, very, very terrible. Why? Well, because it can't overcome the duct's resistance. This is the difference between passing your exam and diagnosing properly on site. Now, let's switch from air to water. Centrifugal pumps. You'll see these everywhere. Domestic systems, commercial plant rooms, agriculture, industry. They're the backbone of fluid movement. And again, the principle is almost identical to the fan. Low pressure at the inlet, high pressure at the outlet. Water gets pushed through the pipes. But here's where students often miss something important. Pumps are sized based on system resistance, not just distance. So if you've got narrow pipes, lots of fittings, valves and height changes, all of these add to resistance. And if your pump can't overcome it, well, you get very poor flow, noise or total failure. I remember a job where someone replaced a pump with a similar one. Looked the same pipe connections. They didn't check the head pressure ratings. Systems never work properly again. That's the difference between guessing and understanding.
If you're enjoying this podcast, please leave us a review.
Now let's step it up. Multi-stage pumps. These are serious bits of kit. You'll see these in high-rise buildings and large commercial systems. Instead of one impeller, you've got multiple stages. Each stage increases pressure further. Think of it like climbing stairs instead of jumping to the top floor in one go. By the time the water leaves the final stage, it's under massive pressure. That's how you get water to the top of a tall building. All right, now we're getting into combustion, and this is where safety, efficiency and understanding all come together. Let's start simple. Atmospheric gas burners. These rely on a Venturi effect. Gas flows into a narrow section, speeds up, creates a vacuum, pulls air in. No fan needed, simple, reliable, widely used, but not always the most efficient. Now compare that to a blown glass burners. These actively push air in using a fan. Why does that matter? Well, because you get better mix of air to gas, more complete combustion, and a higher efficiency. This is what you will need to see in large boilers and commercial setups. Now let's talk oil. Pressure jet burners. This is one of the most impressive bits of engineering you'll come across early in your career. Oil is pumped at high pressure, falls through a tiny nozzle, turned into a fine mist or atomization, mixed with the air and ignited with electrodes. The fine mist is key. More surface area equals better combustion. Now listen carefully, this part matters. Every one of these systems has safety devices, thermal couples, flame rectification, and photoelectric sensors. If a flame goes out, fuel supply stops immediately, because if it didn't, you'd get unburnt gas or oil buildup, and that's how explosions can happen. So when you're learning this, don't just memorize it, understand it, because one day you're responsible for someone's home. Now, heat pumps. If you're a student right now, this is your opportunity. This is where the industry is heading. Let's simplify it. A heat pump doesn't create heat, it moves it. Using the vapor compression cycle, we have the evaporator, which absorbs the heat. We have the compressor that increases pressures and temperatures. The condenser releases heat into the building, and the expansion valve resets the cycle. So let's start off with ground source heat pumps. Think ground source heat pumps. Even in the dead of winter, the ground 2 meters down stays at a pretty constant temperature. We bury cylinder pipes or drill 100-meter boreholes to suck that low-grade heat out of the earth. Then you've got air source heat pumps. They sit outside the house. They look like big fans. They take the energy from the outside air even when it's cold, and moves it inside. Here's the trick for installers. Heat pumps usually run at lower temperatures than old school gas boilers. That's why we often pair them with underfloor heating. It's a slow, steady, comfortable warmth, rather than that scorching earth heat of an old radiator. So don't forget, heat pumps equals lower temperature systems. Instead of blasting heat, they run longer, steadier and more efficiently. That's why underfloor heating works so well with them. Okay, finally, controls, because all this kit is useless without controls. You've got the Y-plan systems with a 1 mid-position valve, or the S-plan systems with separate 2-port valves. Both controlled by programmers, room thermostats and cylinder stats. This is the logic side of plumbing. This is where electrics meet heating, and this is where a lot of apprentices struggle. So my advice is don't avoid it, learn it, because the engineers who understand controls, they're the ones who get called back and paid more. So fans, pumps, burners, heat pumps and controls. This isn't just theory, this is your career. If you take the time to understand this properly, you won't just pass your course, you'll stand out on site. And that's the goal. If this helped you, share it with someone in your class. If you have found this breakdown helpful, do me a massive favour. Hit the follow button on Spotify or wherever you're listening. Share this episode with college classmates or your gaffer. Keep learning, keep grafting, and we will see you in the next episode. I've been Chris Bailey, signing off from the Copper Connection podcast.
We'll be back next week. In the meantime, please subscribe and thanks for listening.